Bismillahirrahmanirrahim. Assalamualaikum everyone. Ramadan Kareem. Today I'm going to talk about biodegradable plastic for our program. Apologize for the sounds distraction because there is a construction work is happening out there. Alright. So our focus today is to know what is it. What is a biodegradable plastic? And the current trends of the utilization of biodegradable plastic and the mechanism involved in making them degraded after being exposed to the environment, or any mechanism involved to make them biodegradable. So, according to this, if you see, this is an introduction. In recent hits, the use of fossil fuel-based plastic has produced production and waste management problems. So these products are low cost, versatile, and highly resistant heat, humidity, sunlight, and microbial contamination. So those are some sort of properties that provide the materials with attractive mechanical, thermal, and barrier properties. However, fossil fuel-based plastics have some problem. And because there are many things that we have to consider when we talk about our environment. One of the main problems is that fossil fuel supplies are unlimited. So when they are limited, therefore cost should increase in the future because they are very limited and we have used it, people are using it, we have certain plan to use this certain amount of fuel based material plastic. So eventually it's going to be faded from the sources. So additionally, use of conventional plastic produces waste management problem, including pollution, poor air quality, and moreover, recycling or incineration processes are complicated and expensive. If you see in the figure that we have on the left, is that this is a review paper that I have read on the degradation mechanism of polylactic acid, hydrolactic, photodegradative, microbial, and enzymatic degradation. So this figure provides information regarding the global plastic waste. Which generated by various type of industrial sectors. um, Not surprisingly, this data show that the packaging industry generates quantities of waste, followed by textile and consumer product industries. So total of waste, if you see at the projected numbers here, million tons, approximately 140 million tons for packaging, followed by textile, consumer product, transportation, electrical, electronic, construction, industrial machinery, and other sectors. So these sectors are definitely very obvious and visible to us, especially when we talk about packaging. So all package now, at least it should have the plastic. So these issues have been discussed many years. Therefore, scientists have actually put many effort to come up with the plastic that are biodegradable. Okay, moving on. If you see in this figure, this review, the similar paper that I have read, this is a global production capacities of biodegradable plastic. Okay, so these are the sources in which that we can produce the biodegradable plastic. We can get from starch blend, about 42% PHE, Other biodegradable 3%, and PBS 11%, PBAT 70%, and some portion of it is PLA, polylactic acid, which is 24%. So 24% is quite a bit of a number, because PLA is one of the famous polymer to be used as the source for producing biodegradable plastic. Okay, allow me to see, to show you, sorry, allow me to show you. This is a table um, to show you that there are many types of biodegradable plastic. And each degradable plastic, each type, have different types or way how to produce it, and what are the advantages and disadvantages of each types of polymer. For instance, if we are taking polylactic acid, today I'm going to talk about polylactic acid because it is very famous and also worldwide known for its compostable advantages. So it's produced by starch, for example, corn or cassava. Okay, we can get the polylactic acid from corn or cassava. And however, there are some drawback of having these materials, which they are brittle, non-biodegradable at ambient temperature. Okay, it cannot be degraded at a normal temperature, which is a room temperature. So, um, another types is polyhydroxyl alkonates, produced by microorganism. For example, Cuprividus nicata. Its advantage include to as it is able to use conventional processing equipment, UV stable, and we know that our packaging are exposed to UV, good resistant to moisture, and aroma barrier properties. However, it is very expensive and low thermal stability causes difficulties during processing. It's not that stable during the process because the process needs the thermal incorporation during the fabrication. Another type is polycaprolactones, PCL. This is one of the famous as well because of my experience that I do much on the biodegradation. PCL is one of the option, one of the good polymer that we can use. However, this is the way how it is being produced. If you see, it is produced by petrochemical products. Its advantages include slow rate of degradation, poor mechanical properties. And however, it is not a good resistant to water, oil, solvent, and chlorine. Okay. Another plastic that we can actually you can read it after, like we have a numerous type of biodegradable polymer. One of it is cellulose bioplastic. Okay, we can get from the plant, which is the cellulose plant. Part of the plant, we take the cellulose out, and it's very easy to process. However, it is expensive and can become thermoplastic when extensively modified. So definitely when we are taking all those degradable plastic, we are taking it from raw, but we have to further process it to make it a plastic. It's not that easy as what we imagine. Okay. So I'm gonna talk about polylactic acid. The application of polylactic acid is very quite wide. Include the transportation, agriculture, electronic industry, textile, biomedical industry, and also the packaging. Packaging is, of course, it is being used. I mean, like any type of biodegradable plastic. Definitely, they are being aimed for packaging. Okay, nowadays PLA is one of the most promising materials for commercially replacing non-degradable materials such as polyethylene, terephthalate, and polystyrene. Okay, so PET and polystyrene definitely are not degradable. So one of the advantage of using PLA is that PLA can be produced. It means that we can produce it. We don't have to rely on the source of the fuel. Fossil fuel that we have to find it somewhere. So this is actually available, for instance, from the plant and etc. Besides, PLA provides adequate energy saving by consuming CO2, carbon dioxide, during production. Another advantage of PLA is recyclable, biodegradable, and compostable. That's definite properties that we want it actually. Yeah. It is important to replace non-degradable plastic with biodegradable plastic in various applications due to environmental awareness. This is one of the statements that are very common for us to know, that we are aiming to produce more biodegradable plastic. Okay. So it shows that the figure here is that these PLA are being used in packaging, transportation, etc. So packaging is the most important application in which that the growing awareness of environmental problems that is associated with the use of non-degradable plastic packaging, um, such as polyethylene, polypropylene, ethylene, vinyl acetate, PET, and PS, as I mentioned earlier. So the drive for scientists and public to find the most suitable or the most available degradable plastic is driven by the awareness. Okay, so the awareness are driven by knowing that these plastic are non-biodegradable and it causes pollution and etc. Okay. In addition, the use of biodegradable materials can reduce the carbon footprints associated with production. PLA has lower carbon footprint than conventional fossil fuel based plastic materials. Thus, the incorporation um, of the biodegradable polymer has the potential to improve food biopackaging materials. Okay. Moving on. Okay. So when we talk about degradation of the plastic, we cannot. We have to we have to know that there are some sort of mechanism involved to degrade the polymer. So now we are talking about the photo degradation. Okay, photo degradation of polymer can be defined as the absorption of the UV radiation by a polymer backbone that leads to the photochemical reaction. It means that the UV that exerted or the plastic is being exposed to UV will have some reaction in which that the UV radiation will be absorbed by the material. So some photochemical reaction will involve, so later the materials will be degraded. Okay, primarily photo degradation mechanisms are initiated by the transformation of the polymer via photoionization, which is in here it says that Norris type. If you see on the figure on the top, type 1, and followed by the polymer chain season Norris type 2 as detailed in 7A. Okay, if you see this figure, this is the photodegradation mechanism. Okay, photodegradation can lead to Norris reactions, cross-linking reaction, or oxidative processes, and various studies have been published worldwide that have investigated the photodegradation of the PLA. In a study by one of the study by Select et al. Also acted as the photosynthesizer and increased chain scission rates as shown in 7B. So this is 7B. Okay, so this is the they introduced OA. Okay, oxalic acid. Sorry, oxalic acid. So in this case, OA can enhance the crystallinity and did not retard biodegradation. So enhance the crystallinity. So although it can act as the photosensitizer, sensitizer, and increase chain sensation rate, as what you see in 7B, this one. This is the figure. It enhances the crystallinity. Crystallinity leads to the stabilization. And in this case, it's not retard for biodegradation. So these are some sort of challenges. We know that definitely it can lead to the photodegradation. That is the basic principle. However, the use of certain, in this case, we want to increase the chain seasons, chain season. We use OA, oxalic acid. So in oxalic acid. So in this case, it is actually increase the chain season rate. However, it also enhance the crystallinity. So why crystallinity is important? Because crystallinity is important for the integrity of the strand. Okay, but it is it goes as in that in this case, OA did not retard the biodegradation. Okay, so it means that the biodegradation can happen, but challenges here is to ensure the OA is sufficient to cross-link the polymer, giving a good strength, but will not degrade it quickly. So some sort of further study is needed to ensure that the integrity of the strand is maintained and sustained after a certain period. Okay. Another type of degradation is microbial degradation. It is very annoying. The sounds out there, the construction, but I have to do the recording in any cases. Okay. This is the schematic diagram of biochemical processes in PLA degradation. Okay. Okay. Microbial degradation is described as the microbial conversion of organic compounds to less toxic or more useful forms in either the laboratory or in natural environment. Okay, so the mechanism initiated after the high molecular weight of PLA undergoes hydrolysis. The first step is the hydrolysis. If you see in the figure A, okay, it shows the schematic diagram of the microbial degradation of PLA. So this is the mechanism involved. Typically, inducer such as gelatin, elastic, fibrin, and some amino acids and peptides are needed to stimulate the process. So after intermolecular ester links of PLA are targeted by a depolymerase, oligomers, dimers, and monomers are produced. And microbial membranes can infiltrate low molecular weight compound. So we started by high molecular weight and by hydrolysis, and then more breaking of the bond in between the polymers is happening stage by stage. Okay, as a result, intercellular enzyme decompose the PLA to carbon dioxide, water, or methane. In comparison to other biodegradable materials, PLA requires a long time to be degraded in soil because PLA is resistant to microbial attack. Okay, several studies have reported the increasing of the rate of PLA biodegradation by incorporating a microbial consortium containing mesophilic bacteria, actinomycete, and etc. Okay, as well as organic waste and dairy manure within the soil. So there are many challenges, but this is the thing that we can understand at the moment. We started from the high molecular weight of the plastic, and how does this polymer is being uh, broken their chains according to certain stages. Okay, so eventually the plastic will be degraded by the reaction of the bacteria. Okay. Another types of degradation is that this enzymatic degradation. Okay, this is a figure showing the PLA degrading enzyme. Okay, and B is the proposed scheme of biodegradation process of PLA film by enzymatic activity produced by PLA degrading bacteria. And this is the optical microscope images of the degraded sample in alpha amylase in different times. So yes, we can make the plastic degradable using certain mechanism. In this case, it is enzymatic degradation. Okay, enzymes capable of hydrolyzing PLA include lipase, esterase, and alkalis. Okay, the optimum pH values, temperature, chain stereochemistry, and materials crystallinity are factors that influence the maximum activities of these enzymes. Okay, and the optimum environment factors as well as those suitable microorganism are the most important component affecting PLA biodegradation in the environment. So there are numerous studies have been conducted in the past regarding the enzymatic degradation of PLA using proteinase, lipase, and cutinase type enzyme. One of the report, I think the in here is stated the first report was published in 1981 by William from University of Liverpool, which assessed the enzymatic degradation of PLA by proteinase K from Titiraceum Titiraceum album. So this is one of the bacteria. Enzyme. Afterward, a number of studies of the enzymatic degradation of PLA were reported, which include work contributed to the establishment of the 56 commercially available proteases. Okay, so protease, these are the enzyme. Finding indicated that some alkaline protease produce considerable quantity of lactic acid from PLA, while acid and neutral protease have little to no activity. So it means that in here that the alkaline condition or environment will help for the degradation of the PLA to the lactic acid. Okay. So, as a result of the limited condition within which commercial proteins are effective, they cannot be applied to degrade PLA plastic under typical environment condition. Therefore, modern molecular biology and technique must be used to purify and characterize extracellular PLA degraded enzyme from microorganisms using UV spectroscopy, sodium dosyl sulfate, polyacrylamide, gel electrophoresis, and 16S RNA analysis. So this is reports that have been published to show you that there are some possibilities in which that we can make the polymer degraded. However, still to date, there are many challenges from time to time. The well-established plastic of the degradable one are still being tuned or fine-tuned from time to time, so that eventually our target to make the polymer degradable will be achieved. Alright, thank you for today. Assalamualaikum warahmatullahi wabarakatuh.